Tonight, we're venturing beyond the familiar boundaries of our solar system, past the gentle giants we call Jupiter and Saturn, into the infinite darkness where something so massive, so impossibly large exists that it challenges everything we thought we knew about planetary formation. We're talking about the largest planet ever discovered in our universe, a world so enormous that it makes Jupiter look like a marble floating in an ocean. The visuals are here to guide you through this celestial voyage, but feel free to close your eyes. Let your imagination soar and drift among the stars at the speed of wonder itself. What I'm about to share with you will reshape your understanding of what's possible in our universe. We'll journey to a world so massive that its very existence was once thought impossible. A planet that stretches the laws of physics to their absolute limits and forces us to rewrite the textbooks on how worlds can form and survive in the cosmic arena. The story begins not with what we can see, but with what we cannot. For thousands of years, humanity has looked up at the night sky and wondered what lies beyond the wandering stars we call planets. We knew of the 5 classical planets visible to the naked eye, those ancient lights that moved against the backdrop of fixed stars. Mercury, Venus, Mars, Jupiter, and Saturn danced across our skies, their motions carefully tracked by civilizations that understood their significance long before we knew what they truly were. But the universe, as we've learned time and again, is far stranger and more magnificent than our earthbound perspectives could ever imagine. Hidden in the depths of space, orbiting distant suns in solar systems we're only just beginning to discover, exist worlds that dwarf anything in our cosmic neighborhood. Planets so large they blur the line between world and star, so massive they bend the very fabric of space around them. The largest planet ever discovered carries a designation that sounds more like a code than a name. Astronomers call it ROXs 42BB, though some know it by its more technical catalogue number. This world exists in a realm so distant that its light has travelled for over 400 years to reach our telescopes. When the photons now hitting our detectors began their journey across the cosmos, Shakespeare was writing his greatest works, and Galileo was pointing his primitive telescope at the moons of Jupiter for the very first time. But here's what makes this discovery so extraordinary, so fundamentally challenging to our understanding of planetary science. ROXs 42 BB isn't just large in the way Jupiter is large compared to Earth. This world is so massive that it contains approximately 9 times the mass of Jupiter packed into its enormous frame. To put this in perspective, Jupiter itself is more than twice as massive as all the other planets in our solar system combined. Now imagine something 9 times more massive than that cosmic giant. The numbers become almost abstract when we try to comprehend the true scale of this world. If Earth were the size of a marble, Jupiter would be roughly the size of a basketball. ROX 42BB would be a sphere so large you could barely wrap your arms around it. But mass tells only part of this incredible story. The sheer volume of this planetary giant defies easy comparison. This world is so large that if you could somehow place it at the center of our solar system, where the Sun currently resides, its surface would extend far beyond the orbit of Mercury. The entire innermost region of our solar system, the space where our closest planetary neighbor circles our star, would be completely engulfed by this single, massive world. Standing on the surface of such a planet, assuming you could somehow survive the crushing gravitational forces, the horizon would curve away from you so gradually that it would seem almost flat, stretching endlessly in all directions like an infinite landscape. But perhaps the most mind-bending aspect of ROXs 42BB isn't its size, but its age. This colossal world is remarkably young in cosmic terms, only about 2 million years old. In the grand timeline of the universe, this planet is practically a newborn, formed when our own species was still millions of years away from taking its first steps on the African savanna. Yet, in those brief 2 million years, gravitational forces and the physics of planetary formation have sculpted a world so massive it challenges our fundamental understanding of how planets can grow. The discovery of ROXs 42BB emerged from years of painstaking observation using some of humanity's most sophisticated astronomical instruments. Astronomers didn't find this world by looking for the tiny dip in starlight that occurs when a planet passes in front of its host star, the method we use to detect most exoplanets. Instead, they found it through direct imaging, actually capturing photons of light from the planet itself as it orbits its distant sun. This feat of cosmic detective work required blocking out the overwhelming brightness of the host star, like trying to spot a firefly next to a searchlight from thousands of miles away. The techniques developed to accomplish this represent some of the most advanced optical technology ever created, pushing the boundaries of what's possible when we reach across the vast distances of space to study worlds we can never visit. What makes direct imaging so challenging is the incredible difference in brightness between stars and planets. Stars generate their own light through nuclear fusion, burning with the power of millions of hydrogen bombs every second. Planets, by contrast, only reflect the light of their parent stars or emit their own faint thermal radiation. The difference in brightness is so extreme that detecting a planet next to its star is like trying to spot a grain of sand next to a lighthouse beam while standing on a mountaintop 50 miles away. Yet somehow, through the combined efforts of multiple observatories and years of careful observation, astronomers managed to capture direct images of ROXs 42BB. These images reveal a world glowing with its own heat, still warm from the violent processes that formed it. The planet appears as a faint reddish point of light, separated from its host star by a distance roughly equivalent to the space between our Sun and Neptune. The host star itself, designated ROXs 42b, is a young red dwarf located in the constellation Ophiuchus, the Serpent Bearer. This stellar nursery region is known for its abundance of newly formed stars and the complex dance of gas and dust that gives birth to planetary systems. The entire system exists in what astronomers call a stellar association, a loose group of stars that form together from the same vast cloud of interstellar material. But the relationship between ROXs 42BB and its host star presents another puzzle that challenges our understanding of planetary formation. The planet orbits its star at a distance of approximately 157 astronomical units. To put this in perspective, 1 astronomical unit is the average distance between Earth and the Sun. This means ROXs 42BB orbits its star at a distance more than 5 times farther than Neptune orbits our Sun. This enormous orbital distance raises profound questions about how such a massive planet could have formed so far from its host star. Traditional theories of planetary formation suggest that the largest planets should form closer to their stars, where there's more material available in the protoplanetary disk. The outer regions of young solar systems typically contain less dense material, making it difficult to accumulate enough mass to build such a giant world. The existence of ROXs 42b suggests that our models of planetary formation may need significant revision. Perhaps massive planets can form through different mechanisms than we previously understood. Some astronomers propose that this world might not have formed through the traditional process of gradual accretion, where small particles of dust and ice slowly clump together over millions of years. Instead, it might have formed through direct gravitational collapse, where a region of the protoplanetary disk became so dense that it collapsed under its own gravity, much like the formation of a star. This alternative formation mechanism would explain both the planet's enormous mass and its distant orbit. If ROXs 42b formed through gravitational collapse, it could have grown to its current size much more quickly, and in a region where traditional planet formation would struggle to produce such a massive world. The implications of this discovery extend far beyond a single extraordinary planet. ROXs 42b represents a new class of worlds that exist at the boundary between planets and brown dwarfs. Those failed stars that never quite accumulated enough mass to ignite nuclear fusion in their cores. Understanding how such massive planets form and evolve provides crucial insights into the diversity of worlds that exist throughout our galaxy. As we continue our exploration of this cosmic giant, we'll discover how its very existence is reshaping astronomy and opening new windows into the incredible variety of worlds that populate our universe. The temperature readings from ROX 42b tell a story of a world still glowing with the heat of its violent birth. Infrared observations reveal surface temperatures reaching nearly 1,800 degrees Celsius, hot enough to melt copper and turn sand into glass. This isn't the gentle warmth of reflected starlight, but the deep, primordial heat that radiates from within the planet itself, a testament to the incredible energies involved in forming such a massive world. Imagine standing on the surface of this blazing giant, if such a thing were possible. The sky above would glow with a dull red radiance, not from any sun, but from the very atmosphere around you. The air itself would shimmer with heat, and the ground beneath your feet would pulse with thermal energy rising from the planet's core. This is a world where the boundary between solid surface and atmosphere becomes blurred, where the immense gravitational pressure creates conditions unlike anything we experience in our solar system. The atmospheric composition of ROXs 42b presents another fascinating puzzle for astronomers. Spectroscopic analysis of the light filtering through its atmosphere reveals the presence of water vapor, carbon monoxide, and various complex molecules that form in the extreme temperatures and pressures of this alien world. These atmospheric signatures provide a chemical fingerprint that helps us understand not just what this planet is made of, but how it formed and evolved over its brief 2 million year existence. The gravitational forces on ROXs 42b are so intense they would be instantly lethal to any Earth-based life form. The surface gravity is estimated to be at least 30 times stronger than Earth's gravity. If you weigh 150 pounds on Earth, you would weigh nearly 4,500 pounds on this massive world. Your bones would crumble under the pressure, and the simple act of lifting your arm would require superhuman strength. Even the atmosphere itself is compressed into a dense, almost liquid-like state near the surface, creating conditions that challenge our understanding of where a planet's atmosphere ends and its surface begins. But perhaps the most remarkable aspect of ROX 42Bb isn't its current state, but what it tells us about the future evolution of massive planets. This world sits right at the theoretical limit of what we can call a planet, before it crosses into the realm of brown dwarfs. At 9 Jupiter masses, it's dancing on the edge of a cosmic boundary, massive enough that it might one day begin fusing deuterium in its core, a process that would technically transform it from a planet into a substellar object. The discovery of ROXs 42Bb has forced astronomers to reconsider the very definition of what constitutes a planet. Traditional definitions focus on objects that orbit stars and have cleared their orbital paths of debris. But when a world becomes so massive that it begins to blur the line between planet and star, these definitions become inadequate. Some astronomers now propose that we need entirely new categories to describe worlds like ROXs 42Bb, objects that exist in the grey area between planetary and stellar physics. The search for planets like ROXs 42Bb requires some of the most advanced technology ever created. The telescopes used to detect and study this world employ adaptive optics systems that can correct for the turbulence in Earth's atmosphere thousands of times per second. These systems use deformable mirrors that change shape hundreds of times faster than the blink of an eye, compensating for the atmospheric distortions that normally make it impossible to see such faint objects clearly. The coronagraph instruments that block out the light from the host star are marvels of precision engineering. They must suppress the starlight by factors of millions or billions while preserving the faint signal from the orbiting planet. This is equivalent to blocking out the glare of a car's headlights while trying to spot a candle flame positioned just inches away from the headlight. The technical challenges involved in achieving this level of precision have pushed optical engineering to its absolute limits. Ground-based observatories around the world have contributed to our understanding of ROXs 42Bb. The Keck Observatory in Hawaii, with its twin 10-meter mirrors, has provided crucial infrared observations that reveal the planet's temperature and atmospheric composition. The Very Large Telescope in Chile, with its sophisticated adaptive optics system, has captured some of the clearest images of this distant world. Each observation adds another piece to the puzzle of understanding how such massive planets form and evolve. But the study of ROXs 42Bb extends beyond just this single world. Astronomers have discovered that massive planets like this one might be more common than we previously thought. Wide-orbit giant planets, worlds that circle their stars at enormous distances, appear to represent a significant population of exoplanets that we're only just beginning to understand. These discoveries suggest that our solar system, with its relatively compact arrangement of planets, might be the exception rather than the rule. The formation timeline of ROX 42Bb challenges many of our assumptions about how quickly massive planets can assemble. Traditional models suggest that it should take tens of millions of years for a planet to grow to such enormous size through the gradual accumulation of smaller objects. Yet ROXs 42Bb accomplished this feat in just 2 million years, implying formation mechanisms that operate much more rapidly than we previously understood. One possibility is that ROXs 42Bb formed through disk instability, a process where regions of the protoplanetary disk become gravitationally unstable and collapse directly into planetary mass objects. This mechanism could explain how such a massive planet formed so quickly and at such a great distance from its host star. The gravitational collapse would have released enormous amounts of energy, heating the newly formed planet to the extreme temperatures we observe today. The orbital dynamics of ROXs 42Bb also provide insights into the early history of planetary systems. Computer simulations suggest that massive planets like this one can significantly influence the formation and evolution of other worlds in their systems. Their gravitational influence can scatter smaller objects throughout the system, potentially disrupting the formation of Earth-like planets in the habitable zone around the host star. The long orbital period of ROXs 42Bb, estimated to be over 1,700 Earth years, means that astronomers have observed only a tiny fraction of its orbit around its host star. We're essentially taking a snapshot of this world at one moment in its incredibly long year. Future observations over the coming decades will reveal how the planet's brightness and temperature change as it moves through different phases of its orbit, providing additional clues about its atmospheric dynamics and internal structure. The study of massive exoplanets like ROXs 42Bb has implications that extend far beyond planetary science. These worlds serve as natural laboratories for studying extreme physics under conditions that cannot be replicated on Earth or in our solar system. The intense gravitational fields, extreme temperatures, and unusual atmospheric compositions provide opportunities to test our understanding of matter and energy under conditions that push the boundaries of known physics. The discovery of ROXs 42Bb also raises intriguing questions about the potential for life in systems containing such massive planets. While the giant planet itself is far too hot and massive to support life as we know it, its gravitational influence might affect the formation and evolution of smaller, potentially habitable worlds elsewhere in the system. The complex gravitational dance between massive planets and smaller worlds could create unique conditions that either enhance or inhibit the development of life. As our observational capabilities continue to improve, astronomers expect to discover many more worlds like ROXs 42Bb. The next generation of space-based telescopes will have the sensitivity and resolution needed to detect and study massive exoplanets around a much larger sample of nearby stars. These future discoveries will help us understand whether ROXs 42Bb represents a rare cosmic oddity or a common type of world that exists throughout our galaxy. The story of ROXs 42Bb reminds us that the universe consistently exceeds our expectations and challenges our understanding of what's possible. This single world, orbiting a distant star in a young stellar nursery, has forced astronomers to reconsider fundamental questions about planetary formation, the definition of planets themselves, and the incredible diversity of worlds that populate our cosmic neighborhood. Woo. The mysteries surrounding ROXs 42Bb deepen when we consider the delicate balance that allows such a world to exist at all. This planetary giant occupies a razor's edge in the cosmic order, massive enough to rival the smallest stars yet still bound by the gravitational embrace of its parent sun. The physics governing its existence operate in realms where our terrestrial understanding begins to break down, where the familiar rules that govern Earth-sized worlds give way to exotic processes that blur the boundaries between planetary and stellar physics. What captivates astronomers most about this colossal world is its position in what scientists call the deuterium burning limit. At 9 Jupiter masses, ROX 42Bb hovers tantalizingly close to the threshold where nuclear processes might begin to stir within its core. Deuterium, a heavy isotope of hydrogen, can begin fusing at much lower temperatures and pressures than regular hydrogen. If ROXs 42Bb were just slightly more massive, perhaps 12 or 13 Jupiter masses, it would cross this cosmic Rubicon and begin generating its own nuclear energy, transforming from planet to brown dwarf in the process. This precarious position makes ROXs 42Bb a natural experiment in the fundamental forces that shape our universe. The planet exists in a state of barely contained gravitational collapse, where the inward pull of its own immense mass is balanced against the outward pressure of its superheated interior. This delicate equilibrium has persisted for 2 million years, creating a world that challenges our understanding of how matter behaves under extreme conditions. The internal structure of this massive planet likely differs dramatically from anything in our solar system. Deep within its core, pressures may exceed those found at the center of the Earth by factors of hundreds or thousands. Under such extreme conditions, hydrogen itself may exist in metallic form, a state of matter that transforms the lightest element into something resembling liquid metal. This metallic hydrogen core would be surrounded by layers of compressed gases and exotic materials that exist nowhere else in our cosmic neighborhood. The magnetic field generated by such a world would dwarf anything we can imagine. Jupiter's magnetic field is already thousands of times stronger than Earth's, powerful enough to trap charged particles in radiation belts that would be instantly lethal to any spacecraft venturing too close. ROX 42Bb's magnetic field would be correspondingly more intense, creating a magnetosphere so vast it might extend millions of kilometers into space. This invisible shield would deflect stellar winds and cosmic radiation with such force that it could influence the very fabric of space around the planet. Recent computer simulations have attempted to model the atmospheric dynamics of such massive worlds, revealing weather patterns that defy earthly comparison. The combination of rapid rotation, intense heat, and crushing gravity would create atmospheric currents moving at speeds that make Earth's most violent hurricanes seem like gentle breezes. Storms on ROXs 42Bb might persist for centuries, driven by thermal engines powered by the planet's internal heat. These atmospheric tempests would be large enough to swallow entire Earth-sized worlds, churning through the thick atmosphere with energies that rival the total power output of our Sun. The observational challenges involved in studying ROXs 42Bb have pushed astronomical instrumentation to unprecedented levels of sophistication. The planet's faint infrared glow must be separated from the overwhelming brightness of its host star using techniques that border on the miraculous. Astronomers employ arrays of telescopes working in perfect synchronization, combining their signals to create virtual instruments with resolving power that exceeds what any single telescope could achieve. These interferometric techniques allow researchers to peer across hundreds of light-years of space with clarity sharp enough to distinguish features on the planet's surface, if such features exist. The discovery process itself reads like a detective story spanning multiple years and international collaborations. Initial observations suggested the presence of a massive companion to the young star ROXs 42b, but confirming its planetary nature required painstaking analysis of its motion, temperature, and spectral characteristics. Astronomers had to rule out the possibility that they were seeing a background star, a brown dwarf, or some other celestial imposter before they could declare the discovery of this planetary giant. The implications of ROXs 42b's existence extend far beyond the boundaries of our current solar system. This world serves as a window into processes that may have shaped the early history of our own cosmic neighborhood. During the formation of our solar system 4.5 billion years ago, Jupiter itself might have grown to similar proportions before gravitational interactions with other forming planets limited its growth. The discovery of ROXs 42b suggests that in systems where such interactions don't occur, planets can grow to truly staggering sizes. The chemical composition of this massive world tells a story of formation from the primordial materials that existed in the early universe. Spectroscopic analysis reveals the presence of heavy elements forged in the hearts of previous generations of stars, materials that were scattered into space by ancient supernovae and incorporated into the forming planetary system. These elements, though present in tiny quantities compared to the dominant hydrogen and helium, play crucial roles in determining the planet's structure and evolution. The thermal evolution of ROXs 42b follows a trajectory unlike anything in our solar system. While planets like Earth cool gradually over billions of years, massive worlds like this one follow a different path. The planet continues to contract under its own gravity, converting gravitational potential energy into heat through a process that will continue for millions of years. This ongoing contraction keeps the world hot and luminous long after its formation, making it detectable across the vast distances of interstellar space. The discovery of ROXs 42b has catalyzed a revolution in our understanding of planetary demographics throughout the galaxy. Surveys of nearby star-forming regions have revealed that massive, wide-orbit planets may be far more common than previously suspected. These worlds, invisible to traditional planet-hunting techniques that focus on planets orbiting close to their stars, represent a hidden population that could number in the millions throughout our galaxy alone. The formation environment of ROXs 42b provides insights into the chaotic conditions present in young stellar nurseries. The Ophiuchus star-forming region where this system resides is a cosmic construction zone, filled with newborn stars, protoplanetary disks, and the complex interplay of radiation and gravity that shapes emerging planetary systems. The intense ultraviolet radiation from nearby massive stars could have influenced the formation of ROXs 42b, either by heating the protoplanetary disk or by stripping away lighter elements during the planet's assembly. The long-term fate of this massive world remains an open question that fascinates astronomers. Over billions of years, ROXs 42b will continue to cool and contract, possibly developing a more traditional planetary atmosphere as its surface temperatures decrease. However, its enormous mass ensures that it will remain warm for far longer than any conventional planet. Even after the Sun has exhausted its nuclear fuel and begun its death throes, ROXs 42b may still glow faintly in the infrared, a cosmic ember marking the location of its long-dead stellar system. The gravitational influence of such a massive planet extends throughout its entire stellar system, shaping the orbits and evolution of any other worlds that may exist there. Computer models suggest that the presence of ROXs 42Bb would create complex resonances and gravitational perturbations that could either stabilize or destabilize the orbits of smaller planets. These effects might explain why some stellar systems contain multiple planets in stable configurations, while others appear to have been stripped bare by gravitational chaos. The search techniques that led to the discovery of ROXs 42Bb represent just the beginning of our exploration of massive exoplanets. Future space-based observatories will possess the sensitivity to detect and characterize hundreds or thousands of similar worlds, creating a comprehensive census of giant planets throughout our galactic neighborhood. These surveys will reveal whether ROX42Bb is truly exceptional or merely the first of its kind to be discovered. The atmospheric chemistry of this massive world continues to yield surprises as observational techniques improve. Recent observations have detected complex molecules in its atmosphere that form only under specific temperature and pressure conditions. These molecular signatures provide a forensic record of the planet's formation and evolution, allowing astronomers to reconstruct the conditions present during its violent birth 2 million years ago. The study of ROXs 42Bb has also advanced our theoretical understanding of planetary atmospheres under extreme conditions. The combination of high gravity, intense heat, and rapid rotation creates atmospheric dynamics that push existing models to their limits. Researchers have developed new computational techniques to simulate these exotic conditions, creating virtual laboratories where they can explore the behavior of matter under circumstances that exist nowhere else in our solar system. The magnetic environment around ROXs 42Bb likely creates spectacular auroral displays that dwarf anything visible on Earth or even Jupiter. The interaction between the planet's powerful magnetic field and charged particles from its host star would generate electromagnetic phenomena of incredible intensity and beauty. These auroras might be visible across the entire electromagnetic spectrum, creating light shows that could be detected by future telescopes as indirect evidence of the planet's magnetic field strength. The discovery timeline of ROXs 42Bb illustrates the patience and persistence required for modern astronomical research. Initial hints of the planet's existence appeared in observations taken more than a decade ago, but confirming its nature required years of follow-up observations using multiple telescopes and analytical techniques. This extended process of discovery reflects the incredible precision required to tease out the faint signals of distant worlds from the cosmic noise that fills our universe. As we prepare to delve even deeper into the mysteries of this cosmic giant, we find ourselves standing at the threshold of understanding worlds that stretch our imagination to its very limits. ROX 42Bb challenges us to expand our conception of what planets can be, forcing us to grapple with questions that push the boundaries of physics and planetary science into uncharted territory. The mysteries surrounding ROX 42Bb extend beyond its physical characteristics into realms that challenge our fundamental understanding of cosmic architecture. When we attempt to comprehend the formation of such a massive world, we encounter paradoxes that force us to reconsider everything we thought we knew about how planets come into existence. The traditional model of planetary formation, where small particles gradually accumulate over millions of years, seems inadequate to explain how a world 9 times more massive than Jupiter could assemble in just 2 million years. The gravitational choreography required to create such a giant defies conventional wisdom. In the early stages of planetary system formation, the protoplanetary disk surrounding young stars contains only finite amounts of material. For most planets, this material is spread across vast distances, requiring eons of patient accumulation to build substantial worlds. Yet ROX 42Bb appears to have consumed enormous quantities of this primordial material with startling efficiency, growing to its current size in what amounts to a cosmic instant. This rapid assembly process suggests formation mechanisms that operate on entirely different timescales than those governing smaller worlds. Rather than the gradual snowball effect that created Earth and its terrestrial siblings, ROXs 42Bb may have experienced what astronomers call runaway accretion. In this scenario, once the growing planet reached a critical mass threshold, its gravitational influence became so powerful that it began devouring material at an exponentially increasing rate. Picture the early solar system environment where this giant took shape. The young star ROXs 42b was still surrounded by a thick disk of gas, dust, and ice extending far beyond the current orbital distance of its massive companion. Within this disk, density fluctuations created regions where material began to clump together under gravitational attraction. Most of these clumps would have grown slowly, following the familiar pattern that created rocky planets like Mars and Venus. But in one particular region of this ancient disk, something extraordinary occurred. Perhaps a chance encounter between several large clumps created a gravitational seed massive enough to trigger catastrophic growth. Once this seed reached approximately 10 Earth masses, its gravitational field became strong enough to begin capturing gas directly from the surrounding disk. This marked the transition from terrestrial planet formation to gas giant assembly, but at a scale far beyond anything we observe in our own solar system. The gas capture phase of ROXs 42Bb's formation would have been a spectacular process to witness. Streams of hydrogen and helium flowed toward the growing planet like cosmic waterfalls, heating to incredible temperatures as gravitational energy converted to thermal energy. The infalling material formed a glowing accretion disk around the planet, similar to those that surround young stars, but on a smaller scale. This planetary accretion disk would have shone with its own light, briefly outshining the distant parent star from certain viewing angles. During this violent assembly phase, the temperature and pressure at the planet's core reached conditions that approach those found in stellar interiors. The boundary between the solid core and the surrounding gas envelope became increasingly blurred as the immense pressure compressed hydrogen into exotic states of matter. Deep within the planet's heart, hydrogen may have been squeezed so tightly that it transformed into a metallic liquid, creating a core that conducts electricity like a cosmic dynamo. The magnetic field generated by this metallic hydrogen core would have profound effects on the surrounding space. Charged particles streaming from the young parent star would be captured and accelerated by the planet's magnetosphere, creating radiation belts of incredible intensity. These trapped particles would spiral along magnetic field lines, generating radio emissions powerful enough to be detected across interstellar distances. Future radio telescopes may be able to use these emissions as a way to study the magnetic fields of distant giant planets. The atmospheric evolution of ROX-42b tells a story of gradual cooling and chemical complexity. In its earliest days, when the planet was still hot from formation, its atmosphere consisted mainly of hydrogen and helium at temperatures exceeding several thousand degrees. Simple molecules like hydrogen gas and helium couldn't survive in such conditions, leaving the atmosphere relatively chemically inactive despite its enormous mass. As the planet began to cool over its first million years, more complex chemistry became possible. Water vapor condensed from the hydrogen and oxygen present in the primordial atmosphere, creating the first clouds in this alien sky. Carbon monoxide formed from carbon and oxygen atoms, while methane assembled from carbon and hydrogen. These early atmospheric constituents created a greenhouse effect that helped regulate the planet's temperature as it continued to radiate away the heat from its formation. The current atmospheric composition of ROX-42b represents a delicate balance between ongoing cooling and chemical evolution. Spectroscopic observations reveal absorption lines from water vapor, carbon monoxide, and various hydrocarbon compounds that paint a picture of active atmospheric chemistry. The intense pressure at different atmospheric levels creates distinct chemical zones, each with its own characteristic molecular signatures. Near the planet's surface, assuming such a boundary exists, pressures may be so extreme that familiar gases take on properties more resembling liquids. The atmosphere itself becomes a gradient from gas to liquid to solid as one descends through the layers, creating an environment unlike anything in our terrestrial experience. The transition zones between these phases would host unique chemical processes that could produce compounds impossible to create under normal planetary conditions. The weather patterns on such a massive world would operate on scales that dwarf terrestrial meteorology. Storm systems could persist for centuries, powered by the planet's internal heat and driven by rotation rates that create Coriolis effects of incredible intensity. Atmospheric circulation would be dominated by massive jet streams circling the planet at velocities that make Earth's fastest winds seem gentle by comparison. The seasonal variations on ROX-42b follow a pattern unlike any planet in our solar system. With an orbital period exceeding 1,700 Earth years, the concept of seasons takes on an entirely different meaning. Changes in the planet's distance from its host star during its elliptical orbit would occur so gradually that they might be imperceptible within human timescales. Yet these subtle variations could drive long-term atmospheric changes that reshape the planet's appearance over millennia. The relationship between ROX's 42b and its host star presents another fascinating aspect of this system's dynamics. The planet orbits at a distance where the stellar radiation it receives is minimal compared to the heat it generates internally. This means that ROXs 42b is essentially self-illuminating, glowing with its own thermal radiation, rather than reflecting light from its parent star. In many ways, this makes it more similar to a brown dwarf than a traditional planet. The tidal forces between ROXs 42b and its host star are negligible due to their enormous separation, meaning the planet likely maintains a stable rotation rate determined by its formation history rather than tidal locking. This rotation, combined with the planet's massive size, creates day-night cycles that might last anywhere from several Earth hours to several Earth days, depending on the angular momentum the planet retained from its formation process. The search for additional companions in the ROXs 42b system continues to yield intriguing possibilities. Computer models suggest that other massive planets could exist at different orbital distances, hidden from direct detection by their faintness or unfavorable orbital orientations. The gravitational influence of ROXs 42b itself could have shaped the formation and evolution of these hypothetical siblings, creating a complex family of giant worlds orbiting their distant sun. The discovery techniques that revealed ROXs 42b have opened new avenues for finding similar worlds around other young stars. Direct imaging surveys are now targeting hundreds of nearby stellar nurseries, searching for the faint infrared glow that betrays the presence of massive, recently formed planets. These surveys have already revealed several candidate worlds that may rival or exceed ROXs 42b in size and mass. The technological challenges involved in these searches push optical engineering to its absolute limits. The coronagraph instruments that block out starlight must achieve contrast ratios of billions to 1, while maintaining the stability needed for hours-long exposures. Adaptive optic systems correct for atmospheric turbulence thousands of times per second, creating artificial guide stars using laser beams projected into the upper atmosphere. The data analysis required to confirm planetary discoveries involves sophisticated statistical techniques that separate genuine planetary signals from instrumental artifacts and background contamination. Each candidate planet requires years of follow-up observations to confirm its nature, measure its properties, and rule out alternative explanations for the observed signals. The broader implications of ROX 42b's discovery extend far beyond planetary science into questions about the formation and evolution of stellar systems throughout our galaxy. If massive planets like this one are common around young stars, they could play crucial roles in shaping the architecture of planetary systems during their early evolution. Their gravitational influence could scatter smaller objects throughout their systems, potentially delivering water and organic compounds to inner planets that might later develop conditions suitable for life. The study of ROXs 42b also provides insights into the conditions present in the early universe when the first planetary systems were forming. The heavy elements detected in the planet's spectrum were created by previous generations of stars and scattered into space by supernova explosions. Understanding how these elements are incorporated into forming planets helps us trace the chemical evolution of our galaxy over billions of years. The future observation of ROXs 42b promises to reveal even more secrets about this extraordinary world. Next-generation telescopes will have the sensitivity to study the planet's atmospheric composition in unprecedented detail, potentially detecting biosignature gases that could indicate the presence of life in the upper atmosphere. While life seems unlikely in such an extreme environment, the discovery of complex organic chemistry would have profound implications for our understanding of how life might emerge in unusual cosmic environments. The orbital motion of ROXs 42b around its host star will gradually become apparent as observations continue over the coming decades. Measuring this orbital motion will provide precise measurements of the planet's mass and orbital characteristics, refining our understanding of its formation history and long-term evolution. These measurements will also help astronomers search for additional planets in the system by detecting gravitational perturbations in ROXs 42b's orbit. As we continue to unravel the mysteries of this cosmic giant, each new observation adds another piece to the puzzle of understanding how the most extreme worlds in our universe come to exist. ROXs 42b stands as a testament to the incredible diversity of planetary systems and the surprising ways that gravity, heat, and time can conspire to create worlds that challenge our imagination and expand our understanding of what's possible in the vast theater of space. The story of this remarkable world reminds us that the universe consistently exceeds our expectations, harboring wonders that push the boundaries of physics and planetary science into realms we're only beginning to explore. In studying ROXs 42b, we're not just learning about one extraordinary planet, but gaining insights into the fundamental processes that shape worlds throughout our galaxy and beyond. As we stand at this threshold of understanding, peering across the cosmic abyss toward this magnificent giant, we encounter questions that reach into the very heart of what it means to exist in our universe. ROX 42b challenges us not merely as scientists or observers, but as conscious beings trying to comprehend our place in a cosmos that seems designed to humble our understanding at every turn. Consider for a moment the profound loneliness of this world. Orbiting its distant star every 1700 years, ROXs 42b experiences seasons that span entire civilizations. When this planet last completed a full orbit around its sun, human civilization was just beginning to develop agriculture. By the time it completes its next orbit, assuming humanity still exists, we may have spread to the stars ourselves, or evolved into something unrecognizable from our current form. This temporal scale transforms our understanding of planetary existence into something almost philosophical. What does it mean for a world to experience change so gradually that entire species might rise and fall in what amounts to a single planetary day? The weather patterns we observe today may persist for thousands of human generations, creating atmospheric monuments to forces beyond our comprehension. The gravitational environment around ROXs 42b creates distortions in space-time that would be measurable even from Earth if we possess sufficiently sensitive instruments. Einstein taught us that mass curves the fabric of reality itself, and a world 9 times more massive than Jupiter creates curvatures that approach those found around small stars. Standing on the surface of such a world, if the crushing gravity didn't instantly destroy any visitor, time itself would run measurably slower compared to observers in less intense gravitational fields. This time, dilation effect means that ROXs 42b exists in a slightly different temporal reference frame than the rest of its stellar system. Clocks on the planet's surface would tick more slowly than identical clocks floating in the emptiness between the stars. While the difference would be tiny, it represents a fundamental aspect of how extreme mass shapes not just space, but the very flow of time itself. The electromagnetic environment surrounding this massive planet creates phenomena that stretch our understanding of planetary magnetospheres into new territory. The interaction between the planet's powerful magnetic field and the sparse but continuous stream of particles from its host star generates auroral displays that could span entire continents. These auroras would be visible not just in the familiar green and red of Earth's northern lights, but across the entire electromagnetic spectrum. creating a symphony of light that extends from radio waves through visible light and into X-rays. The radio emissions from ROXs 42Bb's magnetosphere might be detectable by sensitive radio telescopes on Earth, providing another window into the planet's magnetic environment. These emissions would carry signatures of the planet's rotation rate, magnetic field strength, and the density of charged particles trapped in its radiation belts. Future radio surveys might discover dozens of similar worlds by listening for their electromagnetic songs across the cosmos. The internal structure of this colossal world defies easy categorization. Deep within its core, pressures exceed those found at the center of Earth by factors that challenge our understanding of matter itself. The hydrogen that makes up the bulk of the planet's mass transitions through states of matter that exist nowhere else in our solar system. At the boundary between the rocky core and the metallic hydrogen shell, conditions might create exotic forms of ice that remain solid at temperatures exceeding 1,000 degrees Celsius. The energy budget of ROXs 42Bb tells a story of a world still in the throes of formation. The planet continues to contract under its own gravity, converting gravitational potential energy into heat at rates that dwarf the energy output of all human civilization combined. This ongoing contraction will continue for millions of years, keeping the world hot and luminous long after its host star has settled into a stable main sequence existence. The atmospheric dynamics of such a massive world operate according to principles that extend far beyond terrestrial meteorology. The combination of rapid rotation, intense internal heating, and crushing gravity creates circulation patterns that could persist for geological ages. Storm systems the size of Earth might rage in the planet's atmosphere, driven by thermal engines powered by the heat rising from the world's interior. The chemical evolution occurring in ROXs 42Bb's atmosphere provides insights into processes that may have been important during the early history of our own solar system. The high-temperature chemistry taking place in the planet's upper atmosphere could be creating complex organic molecules through pathways that are impossible under Earth-like conditions. These atmospheric laboratories offer natural experiments in chemistry that we cannot replicate in terrestrial laboratories. The discovery of ROXs 42Bb has profound implications for our understanding of planetary system architecture throughout the galaxy. Traditional theories of planet formation suggest that massive worlds should be rare at large orbital distances, where the density of material in protoplanetary disks becomes too low to support rapid growth. Yet here we have a world that challenges these assumptions, suggesting that alternative formation mechanisms may be more common than previously thought. The gravitational influence of ROXs 42Bb extends throughout its stellar system like an invisible hand, shaping the evolution of any other worlds that may exist there. Computer simulations suggest that the presence of such a massive planet could either protect inner worlds from asteroid impacts by gravitationally deflecting dangerous objects, or conversely, could destabilize the orbits of smaller planets, sending them careening into their host star, or ejecting them into interstellar space. The search for planets similar to ROXs 42Bb has revealed that massive, wide-orbit worlds may represent a significant but previously hidden population of exoplanets. These worlds, invisible to traditional transit surveys that focus on planets orbiting close to their stars, require direct imaging techniques that are only now becoming sophisticated enough to detect them reliably. As our observational capabilities improve, we may discover that giant planets like ROXs 42b are far more common than current estimates suggest. The technological achievements required to study this distant world represent some of humanity's greatest accomplishments in precision engineering and optical science. The telescopes used to observe ROXs 42b must maintain stability at levels that would detect vibrations smaller than the width of an atom, while simultaneously correcting for atmospheric turbulence and blocking out starlight billions of times brighter than the planet itself. The data analysis techniques developed to extract planetary signals from the overwhelming noise of astronomical observations push computational science to its limits. Sophisticated algorithms must distinguish genuine planetary signatures from instrumental artifacts, cosmic ray hits, and the subtle variations in stellar brightness that could mimic planetary signals. Each confirmed detection requires months or years of careful analysis to rule out false positives and extract meaningful physical parameters. The international collaboration required to study ROXs 42b demonstrates the global nature of modern astronomical research. Observations from telescopes in Hawaii, Chile, and around the world are combined with theoretical models developed by researchers on every continent. This distributed approach to science allows humanity to pool its intellectual and technological resources in pursuit of understanding that transcends national boundaries. The educational impact of discovering worlds like ROXs 42b extends far beyond professional astronomy into classrooms and science museums around the world. These discoveries capture public imagination in ways that inspire new generations of scientists and engineers, creating a positive feedback loop that drives continued exploration and discovery. The sense of wonder generated by contemplating such extreme worlds motivates the long-term investments in education and research infrastructure that make future discoveries possible. The philosophical implications of ROXs 42b's existence touch on fundamental questions about the nature of planetary systems and the conditions required for life to emerge. While this particular world is far too extreme to support life as we understand it, its existence demonstrates the incredible diversity of environments that exist throughout our galaxy. This diversity suggests that life, if it exists elsewhere, might take forms and inhabit environments far different from anything we can imagine based on our Earth-centric perspective. The long-term evolution of ROX 42b will unfold over timescales that span the entire future history of our species. Over the next billion years, the planet will gradually cool and contract, possibly developing a more traditional atmosphere as its surface temperatures decrease. The complex interplay between cooling, contraction, and atmospheric evolution will create a natural experiment in planetary physics that will continue long after our Sun has exhausted its nuclear fuel. The study of this remarkable world also provides insights into the ultimate fate of planetary systems throughout the universe. As stars age and eventually die, massive planets like ROXs 42b may be among the last objects to retain their heat and continue glowing faintly in the infrared. These planetary embers could persist for trillions of years, serving as cosmic beacons, marking the locations of long-dead stellar systems in a universe that has grown cold and dark. The legacy of ROX 42b extends beyond its immediate scientific significance into realms that challenge our understanding of cosmic possibility itself. This world serves as a reminder that the universe consistently exceeds our expectations, harboring phenomena that push the boundaries of physics into territories we are only beginning to explore. Each new observation of this distant giant adds another thread to the tapestry of knowledge that connects us to the larger cosmic story of which we are all a part. As we continue our patient observation of this remarkable world, measuring its subtle motions against the stellar background and analyzing the faint light that carries information across hundreds of light-years of space, we participate in one of humanity's greatest adventures. We are cosmic archaeologists, using light as our tool to excavate the secrets of worlds that formed when our own planet was still a molten ball of rock, orbiting a young and violent sun. The story of ROXs 42BB reminds us that we live in a universe of almost infinite creativity, where gravity and time conspire to create worlds that challenge our imagination and expand our understanding of what it means to exist in the cosmic arena. In studying this distant giant, we are not merely observing an exotic world, but engaging in a dialogue with the universe itself, asking questions that probe the deepest mysteries of existence and receiving answers that consistently humble our assumptions about the nature of reality. Each photon that reaches our telescopes from this distant world has traveled for centuries through the empty darkness of space, carrying with it information about conditions and processes that operate on scales far beyond human experience. In capturing and analyzing this ancient light, we become time travelers ourselves, reaching across the vast gulf of space and time to touch something magnificent and alien, yet fundamentally connected to our own cosmic origins. The future holds the promise of even more extraordinary discoveries as our observational capabilities continue to evolve. Next-generation telescopes will possess the sensitivity to detect and characterize hundreds of worlds similar to ROXs 42BB, creating a comprehensive survey of massive planets throughout our galactic neighborhood. These future observations will reveal whether this world represents a rare cosmic anomaly or the first glimpse of a previously hidden population of planetary giants that populate the outer reaches of stellar systems throughout our galaxy. The discovery of worlds like ROXs 42BB forces us to confront the humbling reality that our cosmic neighborhood may be far from typical. As we peer deeper into space and further back in time, we encounter planetary systems that operate according to rules we're only beginning to understand. These observations suggest that the compact, orderly arrangement of planets in our solar system, with rocky worlds nestled close to the Sun and gas giants residing in the outer reaches, may represent just one possible outcome in the grand lottery of planetary formation. The implications extend far beyond academic curiosity. Each new discovery of massive exoplanets reshapes our understanding of how planetary systems evolve and influences our estimates of where life might emerge elsewhere in the galaxy. If giant worlds like ROXs 42BB are common, their gravitational influence could play crucial roles in determining whether smaller, potentially habitable planets can maintain stable orbits in the zones around their host stars where liquid water might exist. The thermal evolution of ROXs 42BB provides a natural laboratory for studying processes that occurred during the early history of our own solar system. 4.5 billion years ago, Jupiter itself was likely much hotter than it is today, glowing with the heat of its formation and gradually cooling over geological time. By studying currently hot worlds like ROXs 42BB, Astronomers can observe these cooling processes in real time, gaining insights into how gas giant planets evolve from their violent births to their eventual cold maturity. The atmospheric chemistry occurring on this distant world operates under conditions that push our understanding of thermodynamics and molecular physics into new territory. The combination of extreme temperatures, crushing pressures, and intense radiation creates an environment where familiar chemical processes are accelerated to extraordinary rates. Reactions that might take millions of years under Earth-like conditions could occur in mere moments in the superheated atmosphere of this massive planet. Recent advances in spectroscopic analysis have revealed the presence of exotic molecules in ROXs 42B's atmosphere that exist nowhere else in our solar system. These compounds form only under the specific combination of temperature, pressure, and chemical abundance found in the atmospheres of supermassive planets. Their detection provides a forensic record of the conditions present during the planet's formation and offers clues about the chemical processes that might have operated in the early solar system. The magnetic field generated by ROX 42Bb creates a protective bubble around the planet that extends millions of kilometers into space. This magnetosphere deflects charged particles from the host star and cosmic radiation, creating a complex electromagnetic environment that influences everything from the planet's atmospheric chemistry to its radio emissions. The interaction between this powerful magnetic field and the sparse interplanetary medium generates phenomena that have no analog in our familiar solar system. The study of planetary magnetospheres on this scale provides insights into processes that operate in more exotic astrophysical environments, such as the magnetospheres of neutron stars and the accretion disks around black holes. The physics governing these interactions scales across many orders of magnitude, from planetary to stellar to galactic levels, suggesting fundamental principles that unite seemingly disparate cosmic phenomena. The rotational dynamics of such a massive world create effects that would be immediately apparent to any hypothetical observer on the planet's surface. The combination of rapid rotation and enormous size generates centrifugal forces that significantly alter the planet's shape, causing it to bulge at the equator and flatten at the poles. This oblate geometry influences everything from the planet's gravitational field to its atmospheric circulation patterns. The tidal forces within the planet itself, generated by differential rotation between the solid core and the surrounding fluid layers, create internal friction that generates additional heat. This tidal heating, similar to the process that keeps Jupiter's moon Io volcanically active, adds to the thermal budget of the planet and helps maintain its high temperature long after formation. The energy dissipated through these internal processes may exceed the total energy output of our Sun, highlighting the incredible scales of energy involved in the dynamics of such massive worlds. The search techniques that enabled the discovery of ROX 42Bb represent a convergence of multiple technological advances in astronomy. Adaptive optic systems that can correct atmospheric distortions thousands of times per second, coronagraphs that can block out starlight while preserving planetary signals, and cryogenic infrared detectors sensitive enough to detect individual photons all contribute to our ability to study these distant worlds. The computational challenges involved in processing the data from these observations require some of the most sophisticated algorithms ever developed for astronomical research. Machine learning techniques originally developed for pattern recognition in other fields have been adapted to identify the subtle signatures of exoplanets hidden in the overwhelming noise of stellar observations. These algorithms must distinguish genuine planetary signals from instrumental artifacts, cosmic ray hits, and the natural variability of the host stars themselves. The international cooperation required for these discoveries demonstrates the global nature of modern astronomical research. Telescopes in different hemispheres work together to provide continuous coverage of target systems, while researchers from multiple institutions contribute their expertise in areas ranging from planetary formation theory to advanced data analysis techniques. This collaborative approach maximizes the scientific return from expensive observational resources while fostering the exchange of ideas and techniques across national boundaries. The educational impact of discovering worlds like ROXs 42b extends far beyond the scientific community into schools and science museums worldwide. These discoveries capture the public imagination in ways that inspire young people to pursue careers in science, technology, engineering, and mathematics. The sense of wonder generated by contemplating such extreme worlds motivates the long-term investments in education and research that make future discoveries possible. The technological spin-offs from exoplanet research have applications that extend far beyond astronomy. The precision optical systems developed for direct imaging of exoplanets have found applications in medical imaging, industrial inspection, and military surveillance. The data analysis techniques pioneered for exoplanet detection have been adapted for use in fields ranging from seismology to financial analysis. These unexpected benefits demonstrate how fundamental research often leads to practical applications that were never anticipated at the outset. The philosophical implications of studying worlds like ROXs 42b touch on some of humanity's deepest questions about our place in the universe. The discovery of such diverse planetary systems challenges anthropocentric views of cosmic evolution and suggests that the conditions that led to the emergence of life on Earth may be far from unique. This perspective encourages a more humble and nuanced understanding of our cosmic significance, while simultaneously highlighting the precious nature of the conditions that allow life to flourish. The future observation of ROXs 42b will unfold over decades as astronomers track its slow orbital motion and monitor changes in its brightness and spectral characteristics. These long-term studies will provide unprecedented insights into the evolution of massive exoplanets and may reveal unexpected phenomena such as large-scale atmospheric changes or the formation of additional companions in the system. The development of next-generation space telescopes specifically designed for exoplanet research promises to revolutionize our understanding of worlds like ROXs 42b. These future observatories will possess the sensitivity to study the atmospheric composition of massive exoplanets in unprecedented detail, potentially revealing the presence of complex organic molecules or even biosignature gases that could indicate the existence of life in the upper atmospheres of these worlds. The search for additional massive exoplanets continues to accelerate as observational techniques improve and survey programs expand to cover larger numbers of nearby stars. Statistical analyses of current discoveries suggest that massive wide-orbit planets may be present around a significant fraction of Sun-like stars, implying that worlds similar to ROXs 42b may number in the millions throughout our galaxy alone. The theoretical models developed to understand the formation and evolution of supermassive exoplanets like ROXs 42b are pushing computational astrophysics into new territory. These simulations must account for complex interactions between gravitational dynamics, thermodynamics, and magnetohydrodynamics across spatial scales, ranging from planetary cores to entire stellar systems. The computational demands of these models require some of the world's most powerful supercomputers, and are driving advances in numerical methods and parallel processing techniques. The chemical evolution models for massive exoplanet atmospheres reveal processes that may have been important during the early history of life on Earth. The high-energy chemistry occurring in the atmospheres of worlds like ROXs 42b could produce complex organic molecules through pathways that differ significantly from those that operate under terrestrial conditions. Understanding these alternative chemical pathways expands our conception of the environments where the building blocks of life might emerge. The study of massive exoplanets also provides insights into the ultimate fate of planetary systems over cosmic time scales. As host stars evolve and eventually exhaust their nuclear fuel, massive planets may be among the last objects to retain significant thermal energy. These slowly cooling worlds could persist as infrared sources for trillions of years, potentially providing energy sources for exotic forms of life that might emerge in the far future of the universe. The gravitational influence of massive exoplanets like ROXs 42b extends throughout their stellar systems in ways that could significantly affect the formation and evolution of smaller, potentially habitable worlds. Computer simulations suggest that the presence of such giants could either enhance the delivery of water and organic materials to inner planets through gravitational perturbations, or conversely, could destabilize planetary orbits and prevent the formation of stable habitable zones. The discovery of ROXs 42b has catalyzed renewed interest in direct imaging techniques for exoplanet detection. Unlike transit photometry, which can only detect planets whose orbits are aligned with our line of sight, direct imaging can potentially detect planets at any orbital inclination. This capability opens up entire populations of exoplanets that remain invisible to traditional detection methods, promising to reveal the true diversity of planetary systems throughout our galaxy. The atmospheric dynamics of supermassive exoplanets operate on scales that dwarf terrestrial weather systems, while following physical principles that extend our understanding of fluid dynamics under extreme conditions. The combination of rapid rotation, intense heating, and crushing gravity creates circulation patterns that could persist for geological ages, driven by thermal engines powered by the planet's internal heat sources. The electromagnetic environments around massive exoplanets create natural particle accelerators that could generate high-energy radiation detectable across interstellar distances. These radiation signatures could provide new ways to study exoplanetary magnetic fields and atmospheric composition, particularly for worlds that are too faint to observe through conventional spectroscopic techniques. As we continue to unravel the mysteries surrounding ROX 42b and similar worlds, we find ourselves participants in one of humanity's greatest intellectual adventures. Each new observation adds another piece to our understanding of how planets form, evolve, and interact with their stellar environments across the vast scales of space and time. These discoveries remind us that we live in a universe of extraordinary creativity, where the interplay of gravity, thermodynamics, and chemistry creates worlds that consistently exceed our imagination. while teaching us fundamental lessons about the nature of cosmic evolution. The story of ROX 42BB represents more than the discovery of a single extraordinary world. It symbolizes humanity's relentless quest to understand our place in the cosmic hierarchy, to map the boundaries of the possible, and to discover the remarkable diversity of environments that exist throughout our galaxy. In studying this distant giant, we engage in a dialogue with the universe itself, asking questions that probe the deepest mysteries of existence and receiving answers that consistently humble our assumptions while expanding our comprehension of reality's infinite potential. The legacy of ROX 42BB extends into territories that challenge our most fundamental assumptions about the nature of planetary existence itself. As we stand at the threshold of deeper understanding, contemplating this cosmic leviathan that drifts through the darkness at distances that render our entire solar system insignificant. By comparison, we encounter questions that probe the very essence of what it means for worlds to exist in our universe. Consider the profound isolation that defines this giant's existence. Separated from its host star by a gulf so vast that light takes nearly 22 hours to travel between them, ROXs 42BB experiences a form of cosmic solitude that defies human comprehension. While Earth completes its familiar dance around the Sun every 365 days, this distant world requires more than 17 centuries to complete a single orbit, moving through space at velocities so gradual that its progress would be imperceptible within human lifetimes. This temporal disconnect transforms our understanding of planetary seasons into something almost mythological. The subtle changes in stellar radiation that drive seasonal variations on this world unfold over timescales that span entire epochs of human civilization. When ROXs 42BB last reached its closest approach to its parent star, our species had not yet learned to cultivate crops or build permanent settlements. By the time it completes its current orbital journey, humanity may have evolved beyond recognition or spread across the galaxy, carrying the knowledge of this remarkable world to distant stars. The thermal signature of ROX 42BB tells a story that extends far beyond simple planetary cooling. Deep within its core, nuclear processes may be stirring that blur the distinction between planet and star. At 9 Jupiter masses, this world hovers at the theoretical boundary where deuterium fusion becomes possible, where the lightest isotope of hydrogen can begin the nuclear dance that powers brown dwarfs and red dwarf stars. The internal temperatures and pressures may be sufficient to trigger sporadic fusion events, creating brief flashes of nuclear energy that add to the planet's already formidable thermal output. These potential fusion processes would transform ROXs 42BB from a cooling planetary remnant into something approaching a failed star. The energy released by deuterium burning could halt or reverse the planet's cooling, maintaining its high temperature for millions of additional years. This nuclear activity would create conditions in the planet's core that exist nowhere else in our solar system, where pressures exceed those at Earth's center by factors of thousands and temperatures rival those found in stellar interiors. The atmospheric composition of this massive world continues to evolve as it slowly cools from its formation temperature. Chemical reactions proceed at rates accelerated by the extreme conditions, creating and destroying molecular species on timescales far shorter than their terrestrial counterparts. The carbon monoxide detected in spectroscopic observations may be constantly recycling through complex chemical pathways, combining with hydrogen to form methane, then dissociating again under the influence of intense heat and radiation. Water vapor in the planet's atmosphere exists under conditions so extreme that it challenges our understanding of this familiar molecule. At the temperatures and pressures found in ROXs 42B's atmosphere, water takes on properties that bridge the gap between gas and plasma, creating states of matter that exist nowhere else in our cosmic neighborhood. These exotic forms of water ice may persist at temperatures exceeding 1,000 degrees Celsius, held in solid form by pressures that dwarf anything achievable in terrestrial laboratories. The magnetic environment surrounding this colossal world creates phenomena that operate on scales approaching those found around small stars. The planet's magnetosphere extends millions of kilometers into space, creating a protective bubble that deflects cosmic radiation and charged particles from its host star. Within this magnetic cocoon, trapped particles spiral along field lines at velocities approaching significant fractions of the speed of light, generating synchrotron radiation across the electromagnetic spectrum. These high-energy processes create auroral displays that would dwarf anything visible from Earth or even Jupiter. The electromagnetic storms raging in ROX 42B's magnetosphere generate radio emissions powerful enough to be detected across interstellar distances, creating a beacon that announces the planet's presence to any civilization possessing sufficiently sensitive radio telescopes. Future surveys of nearby star systems may discover dozens of similar worlds by listening for these electromagnetic signatures rather than searching for their faint optical emissions. The gravitational environment around ROXs 42B shapes spacetime itself in ways that would be measurable even from our distant vantage point. Einstein's general relativity teaches us that massive objects curve the fabric of reality, and a world 9 times more massive than Jupiter creates distortions that approach those found around small stellar objects. These gravitational effects influence the trajectories of any smaller objects in the system, creating complex orbital resonances and perturbations that could persist for millions of years. The tidal forces generated by such an enormous mass extend throughout the planetary system, potentially affecting the formation and evolution of any moons that might orbit this giant world. Computer simulations suggest that ROXs 42B could host a complex system of satellites, ranging from captured asteroids to massive moons that rival the terrestrial planets in size. These hypothetical moons would experience tidal heating so intense that they might remain geologically active for billions of years, creating environments where exotic chemistry and perhaps even primitive forms of life could emerge. The search techniques that led to the discovery of ROXs 42B represent a convergence of multiple technological revolutions in astronomy. The adaptive optics systems that enable direct imaging of such faint objects require real-time correction of atmospheric distortions using deformable mirrors that adjust their shape thousands of times per second. These systems create artificial guide stars by firing powerful lasers into the upper atmosphere, providing reference points for measuring and correcting the turbulence that normally makes high-resolution ground-based astronomy impossible. The coronagraph instruments that block out the overwhelming light from the host star push optical engineering to its absolute limits. These devices must suppress starlight by factors exceeding 1 billion, while preserving the incredibly faint signal from the orbiting planet. The technical challenges involved are equivalent to detecting the light from a candle flame positioned inches away from a searchlight, while observing from thousands of miles away. The precision required approaches the fundamental limits imposed by the wave nature of light itself. The data analysis techniques developed to extract planetary signals from astronomical observations employ some of the most sophisticated algorithms ever created for pattern recognition. Machine learning systems trained on simulated planetary signatures must distinguish genuine detections from instrumental artifacts, cosmic ray hits, and the subtle variations in stellar brightness that could mimic planetary signals. These algorithms process terabytes of observational data, searching for patterns so subtle that they would be invisible to human observers. The international collaboration required to study ROXs S42BB demonstrates the global nature of modern astronomical research. Observations from telescopes in Hawaii, Chile, and around the world are combined with theoretical models developed by researchers across every continent. This distributed approach to science allows humanity to pool its intellectual and technological resources in pursuit of understanding that transcends national boundaries and cultural differences. The educational impact of discovering worlds like ROXs 42BB extends far beyond professional astronomy into classrooms and science centers worldwide. These discoveries ignite the imagination of young minds in ways that inspire new generations of scientists, engineers, and explorers. The sense of wonder generated by contemplating such extreme worlds motivates the long-term investments in education and research infrastructure that make future discoveries possible. The technological innovations driven by exoplanet research have found unexpected applications in fields ranging from medical imaging to industrial inspection. The precision optical systems developed for direct imaging have been adapted for use in surgical microscopes and quality control systems. The data analysis techniques pioneered for exoplanet detection have found applications in everything from seismology to financial market analysis, demonstrating how fundamental research often leads to practical benefits that were never anticipated. The philosophical implications of studying worlds like ROXs S42BB touch on humanity's deepest questions about cosmic significance and the nature of existence itself. The discovery of such diverse planetary systems challenges Earth-centric views of cosmic evolution, while simultaneously highlighting the precious nature of the conditions that allow life to flourish. These discoveries encourage a more nuanced understanding of our place in the universe, one that balances humility with appreciation for the remarkable chain of events that led to our existence. The future observation of ROXs S42BB will unfold over human generations as astronomers track its slow orbital motion and monitor changes in its thermal and spectral characteristics. These long-term studies promise to reveal unprecedented insights into the evolution of massive exoplanets, while potentially uncovering unexpected phenomena such as large-scale atmospheric changes or the formation of additional companions in the system. The development of next-generation space telescopes designed specifically for exoplanet research promises to revolutionize our understanding of worlds like ROXs 42BB. These future observatories will possess the sensitivity to analyze atmospheric composition in extraordinary detail, potentially revealing complex organic chemistry or even biosignature gases that could indicate the presence of life in the upper atmospheres of these exotic worlds. The search for additional massive exoplanets continues to accelerate as survey programs expand to cover thousands of nearby stars. Statistical projections based on current discoveries suggest that massive, wide-orbit planets may exist around a substantial fraction of Sun-like stars, implying that worlds similar to ROXs 42Bb could number in the millions throughout our galaxy alone. The theoretical frameworks developed to understand supermassive exoplanets are pushing computational astrophysics into unexplored territory. These models must account for complex interactions between gravitational dynamics, thermodynamics, and electromagnetic effects across spatial scales, ranging from planetary cores to entire stellar systems. The computational demands require the world's most powerful supercomputers and are driving advances in numerical methods that benefit multiple scientific disciplines. The study of atmospheric chemistry on massive exoplanets reveals processes that may have been crucial during the early evolution of life in our own solar system. The high-energy chemistry occurring in the atmospheres of worlds like ROXs 42Bb produces complex organic molecules through pathways that differ dramatically from those operating under terrestrial conditions. Understanding these alternative chemical routes expands our conception of the environments where the molecular building blocks of life might emerge. The long-term evolution of massive exoplanets provides insights into the ultimate fate of planetary systems across cosmic time. As host stars age and eventually exhaust their nuclear fuel, massive planets may remain warm and active long after smaller worlds have frozen solid. These slowly cooling giants could persist as detectable infrared sources for trillions of years, potentially serving as refuges for exotic forms of life in the far future of a cold and empty universe. The gravitational influence of worlds like ROXs 42Bb extends throughout their stellar systems in ways that profoundly affect the formation and evolution of smaller planets. Dynamical simulations reveal that such massive giants could either protect inner worlds from destructive impacts by deflecting dangerous asteroids and comets, or conversely, could destabilize planetary orbits and prevent the establishment of stable habitable zones where life-supporting conditions might develop. As we continue our patient study of this remarkable world, each new observation adds another thread to the tapestry of knowledge that connects us to the broader cosmic story. ROXs 42Bb serves as a reminder that the universe consistently exceeds our expectations, harboring phenomena that push the boundaries of physics into territories we are only beginning to explore. The study of this distant giant engages us in humanity's greatest intellectual adventure, challenging our assumptions while expanding our understanding of the infinite creativity that characterizes cosmic evolution. In contemplating ROXs 42Bb, we encounter not just an exotic world orbiting a distant star, but a mirror that reflects our own cosmic significance. This massive planet, glowing with the heat of its violent formation in the darkness between the stars, reminds us that we are part of something magnificent and mysterious that extends far beyond the boundaries of our earthly experience. Each photon that reaches our telescopes from this distant realm carries with it a message about the fundamental processes that shape worlds throughout our galaxy, connecting us across space and time to the ongoing story of cosmic evolution that encompasses everything from the smallest quantum particles to the largest structures in the observable universe. The story of ROX 42Bb takes on an almost mystical quality when we consider the precise circumstances that allowed such a world to exist at all. In the vast cosmic lottery of planetary formation, where countless variables must align with mathematical precision, this giant represents a convergence of conditions so unlikely that its very existence challenges our understanding of probability itself. The delicate dance between gravity and thermodynamics that created this world required timing so exact that a difference of even a few thousand years in the formation timeline might have resulted in a completely different outcome. Consider the extraordinary sensitivity of the processes that birthed this colossal planet. The protoplanetary disk surrounding the young star ROXs 42b contained finite amounts of raw material spread across distances measured in billions of kilometers. For ROXs 42b to achieve its current mass, it had to capture and retain nearly 10% of all the hydrogen and helium available in its orbital zone, a feat that required gravitational conditions operating with clockwork precision over hundreds of thousands of years. The temperature gradient within the forming disk played a crucial role in determining where different types of materials could condense and accumulate. Too close to the star, and the intense radiation would have prevented gas capture entirely. Too far away, and the disk density would have been insufficient to support rapid growth. ROXs 42b formed in what astronomers call the sweet spot, a narrow orbital zone where conditions were just right for a planetary embryo to undergo runaway gas accretion. The chemical fingerprints preserved in this world's atmosphere tell a story of formation that unfolded during a brief window when the young stellar system was still in its infancy. Isotopic ratios of carbon, oxygen, and nitrogen locked into the planet's envelope provide a forensic record of the conditions present in the protoplanetary nebula 4.5 million years ago. These ratios reveal details about the temperature, density, and chemical composition of the primordial cloud from which the entire system condensed. The magnetic field environment during ROXs 42b's formation would have been far more chaotic than anything we observe today. The young host star was likely experiencing violent magnetic reconnection events, generating powerful stellar winds and intense radiation bursts that could have stripped away planetary atmospheres if not for the protective influence of the forming planet's own magnetic field. The interplay between stellar and planetary magnetospheres during this critical period may have determined which worlds retained their gaseous envelopes and which were reduced to rocky cores. Recent theoretical work suggests that the formation of supermassive planets like ROXs 42b may be intimately connected to the presence of nearby stellar companions. Computer simulations indicate that gravitational perturbations from other young stars in the birth cluster could have triggered the disk instabilities that led to rapid planetary growth. These external influences might explain why massive planets are often found in stellar systems that originated in dense star-forming regions rather than in isolation. The cooling history of ROX 42b provides insights into processes that operate on timescales far exceeding human civilization. Thermal evolution models suggest that this world has been steadily contracting and cooling for the past 2 million years, yet it remains hot enough to glow brightly in infrared light. The rate of cooling depends critically on the planet's internal structure, particularly the efficiency of heat transport between the core and the surface layers. Deep within the planet's interior, convection currents transport thermal energy from the compressed core toward the cooler outer regions. These convective flows operate on scales that dwarf terrestrial weather systems, with circulation cells that could encompass volumes larger than entire terrestrial planets. The dynamics of these internal flows influence everything from the planet's magnetic field generation to the chemical mixing that determines atmospheric composition. The atmospheric structure of ROX 42b reveals layers of complexity that challenge our understanding of planetary meteorology. Pressure and temperature profiles derived from spectroscopic observations indicate the presence of distinct atmospheric zones, each with its own characteristic chemistry and dynamics. The transition regions between these zones may host exotic cloud formations composed of materials that exist nowhere else in our solar system. High-altitude regions of the atmosphere, where pressures drop to levels comparable to those found on Earth, may contain clouds of exotic ices formed from compounds like titanium dioxide or aluminum oxide. These refractory clouds would create spectacular optical effects, scattering and absorbing light in ways that contribute to the planet's overall thermal balance. The particles within these clouds might grow to substantial sizes under the influence of the planet's intense gravitational field, creating precipitation events that dwarf any terrestrial storm. The search for additional worlds similar to ROXs 42b has revealed tantalizing hints that such giants may be more common than initially suspected. Survey programs targeting young stellar associations have identified several candidate objects that exhibit similar characteristics, including high temperatures, massive sizes, and wide orbital separations from their host stars. Confirming the planetary nature of these candidates requires years of careful observation to rule out alternative explanations such as background stars or brown dwarf companions. The statistical analysis of current exoplanet discoveries suggests that massive planets preferentially form around stars with higher metallicity, meaning stars that contain larger abundances of elements heavier than hydrogen and helium. This correlation provides crucial clues about the formation mechanisms that create worlds like ROXs 42b, indicating that the presence of dust grains and rocky material in protoplanetary disks plays a vital role in triggering the gravitational instabilities that lead to rapid gas accretion. The orbital dynamics of ROXs 42b continue to puzzle astronomers studying the long-term stability of wide-orbit planetary systems. Computer simulations indicate that maintaining a stable orbit at such a large distance from the host star requires very specific initial conditions and an absence of significant gravitational perturbations from passing stars or other massive objects. The fact that this planet has survived for 2 million years in its current configuration suggests either remarkable initial fine-tuning or the operation of stabilizing mechanisms that are not yet fully understood. The tidal interactions between ROXs 42b and any hypothetical moon system would create phenomena unlike anything observed in our solar system. The immense gravitational field of the planet would generate tidal forces capable of maintaining geological activity on moon-sized satellites for billions of years. These tidally heated moons could host subsurface oceans, hydrothermal systems, and complex geological processes that might create environments suitable for exotic forms of life. The electromagnetic environment surrounding this massive world extends its influence far beyond the planet itself, creating a complex web of charged particle interactions that affects the entire local space environment. High-energy electrons and protons trapped in the planet's radiation belts would pose significant hazards to any spacecraft attempting to study the system, requiring shielding technologies far beyond those used for missions to Jupiter or Saturn. The radio emissions generated by ROX 42B's magnetosphere provide a natural laboratory for studying plasma physics under extreme conditions. The acceleration of charged particles to relativistic velocities creates synchrotron radiation that spans frequencies from radio waves through visible light and into X-ray wavelengths. These emissions carry detailed information about the planet's magnetic field structure, rotation rate, and the density of charged particles in its magnetosphere. The discovery techniques that enabled the detection of ROXs 42Bb have opened new avenues for studying planetary formation in real time. Direct imaging surveys can now observe planets that are still hot from formation, providing snapshots of worlds at different stages of their thermal evolution. These observations offer unprecedented opportunities to test theories of planetary cooling and atmospheric evolution against real data from multiple systems. The atmospheric chemistry models developed to interpret observations of ROXs 42Bb have revealed unexpected complexities in the behavior of molecular species under extreme conditions. Chemical equilibrium calculations indicate that the planet's atmosphere should contain a rich mixture of carbon-bearing molecules, including methane, carbon monoxide, and more complex hydrocarbons. The relative abundances of these species provide sensitive probes of the temperature and pressure conditions throughout the atmospheric column. The future study of ROX 42Bb promises to reveal even more secrets about this extraordinary world as observational techniques continue to advance. Next-generation adaptive optics systems will provide higher resolution images that could potentially detect large-scale atmospheric features such as storm systems or temperature variations across the planet's surface. Spectroscopic observations with improved sensitivity may reveal the presence of trace atmospheric constituents that are currently below detection thresholds. The long-term monitoring of this world's brightness and spectral characteristics will provide unique insights into the processes that govern planetary cooling over millions of years. Unlike the planets in our solar system, which have had billions of years to reach thermal equilibrium, ROXs 42Bb offers a rare opportunity to observe planetary evolution in progress. Changes in the planet's temperature and atmospheric composition over human timescales could provide direct evidence of the physical processes that shape massive exoplanets. The search for similar worlds around other young stars continues to expand our understanding of the conditions that favor the formation of supermassive planets. Statistical analyses of current surveys suggest that such worlds may be present around several % of Sun-like stars, implying a substantial population of massive exoplanets that remains largely unexplored. Future survey programs will target thousands of additional stars in nearby stellar associations, potentially revealing dozens of worlds similar to ROXs 42Bb. The technological challenges involved in studying these distant worlds push the boundaries of what is possible with current astronomical instrumentation. The development of space-based telescopes specifically designed for direct imaging of exoplanets represents one of the most ambitious engineering projects ever undertaken by the astronomical community. These future observatories will possess coronagraph systems capable of suppressing starlight by factors of billions while maintaining the stability needed for multi-hour exposures. The scientific legacy of ROX 42Bb extends far beyond its immediate discovery into realms that will influence astronomical research for generations to come. This world serves as a benchmark for testing theories of planetary formation and evolution, providing observational constraints that help refine our understanding of the processes that create the diverse population of exoplanets we observe throughout our galaxy. The study of this remarkable world also highlights the interconnected nature of astronomical research, where discoveries in one field often provide crucial insights into seemingly unrelated phenomena. The techniques developed for studying massive exoplanets have found applications in the study of brown dwarfs, stellar formation, and even the search for potentially habitable worlds around nearby stars. As we continue our exploration of ROX 42Bb and similar worlds, we participate in one of humanity's greatest intellectual adventures. Each observation adds another piece to our understanding of how planets form, evolve, and interact with their stellar environments across the vast scales of space and time. These discoveries remind us that we inhabit a universe of extraordinary diversity and creativity, where the fundamental forces of nature conspire to create worlds that consistently exceed our imagination, while teaching us profound lessons about the cosmic processes that shaped our own planetary home. The story of this distant giant ultimately connects us to the broader narrative of cosmic evolution, reminding us that we are part of an unfolding story that encompasses everything from the formation of the first stars to the emergence of consciousness capable of contemplating its own origins. In studying ROXs 42Bb, we engage with mysteries that probe the deepest questions about existence itself, seeking to understand our place in a universe that continues to reveal new wonders with each passing observation. The profound implications of ROX 42Bb's existence ripple through our understanding of cosmic architecture in ways that transform how we perceive the very nature of planetary formation throughout our galaxy. As we peer deeper into the mysteries surrounding this colossal world, we encounter revelations that challenge the fundamental assumptions upon which modern astronomy has built its theoretical foundations. Consider the remarkable precision required for such a massive planet to maintain its current orbital configuration over millions of years. The gravitational dance between ROX 42Bb and its distant host star operates according to celestial mechanics so delicate that even tiny perturbations could destabilize the entire system. Computer simulations reveal that maintaining stable orbits at such vast distances requires initial conditions fine-tuned to extraordinary precision, where variations of even a few percent in the planet's formation velocity could have sent it careening into interstellar space or spiraling toward its parent star. The thermal equilibrium that governs this world's current state represents a fascinating interplay between competing physical processes. While the planet continues to radiate away the primordial heat from its formation, gravitational contraction adds new thermal energy at rates that vary depending on the complex internal structure. This ongoing contraction creates a feedback mechanism where cooling leads to shrinkage, which generates additional heat, temporarily slowing the cooling process in a cosmic dance that will continue for millions of additional years. Recent advances in atmospheric modeling have revealed unexpected complexities in the chemical processes occurring within ROXs 42Bb's dense envelope. The extreme pressures and temperatures create reaction pathways that simply cannot exist under terrestrial conditions, leading to the formation of exotic molecular species that challenge our understanding of atmospheric chemistry. These reactions proceed at rates accelerated by factors of millions compared to their terrestrial counterparts, creating and destroying complex molecules in time frames measured in hours rather than geological ages. The discovery of this massive world has prompted astronomers to reconsider the efficiency of planetary formation mechanisms throughout the galaxy. Traditional models suggested that building such enormous planets should require tens of millions of years, yet ROX 42Bb accomplished this feat in a fraction of that time. This rapid assembly implies formation processes that operate far more efficiently than previously understood, possibly involving direct gravitational collapse of entire regions within the protoplanetary disk. The magnetic field environment surrounding this colossal planet creates phenomena that blur the boundaries between planetary and stellar physics. The magnetosphere extends so far into space that it effectively creates a magnetic barrier protecting the inner regions of the stellar system from cosmic radiation and charged particles streaming from the host star. This protective influence could play crucial roles in determining the habitability of any smaller worlds that might exist in the system's inner regions. The atmospheric dynamics operating on such a massive world follow patterns that dwarf anything observed in our familiar solar system. Storm systems driven by the planet's internal heat source could persist for centuries, creating weather patterns that operate on timescales comparable to entire epochs of human civilization. These atmospheric disturbances would be large enough to engulf Earth-sized worlds completely, powered by thermal engines that generate more energy than all of human technology combined. The search techniques that enabled the discovery of ROXs 42Bb have opened entirely new avenues for exploring the outer reaches of planetary systems throughout our galactic neighborhood. Direct imaging surveys can now detect massive planets that were completely invisible to previous generation instruments, revealing a population of worlds that may be far more common than current statistics suggest. These discoveries are forcing astronomers to revise their estimates of planetary demographics throughout the galaxy. The chemical composition preserved in this world's atmosphere provides a unique window into conditions that existed during the earliest stages of planetary system formation. Isotopic ratios locked into the planet's gaseous envelope carry information about the temperature and density of the protoplanetary nebula from which the entire system condensed. These chemical fingerprints reveal details about stellar nucleosynthesis processes that occurred in previous generations of stars, connecting this distant world to the cosmic chemical evolution that has unfolded over billions of years. The gravitational influence of ROXs 42Bb extends throughout its stellar system in ways that could profoundly affect the formation and evolution of any additional worlds. The planet's massive gravitational field creates complex orbital resonances that could either stabilize or destabilize the trajectories of smaller objects throughout the system. These gravitational effects might explain the apparent rarity of close-in planets around stars that host massive outer companions. The technological achievements required to study this distant world represent some of humanity's greatest accomplishments in precision engineering and observational astronomy. The instruments capable of detecting such faint objects must maintain stability at levels that approach the fundamental limits imposed by quantum mechanics, while simultaneously correcting for atmospheric distortions that change thousands of times per second. These technological marvels push the boundaries of what is physically possible, with ground-based astronomical observations. The evolutionary timeline of ROX 42Bb provides insights into processes that will unfold over cosmic timescales, far exceeding the entire future history of human civilization. Thermal models indicate that this world will continue glowing in infrared light for hundreds of millions of years, gradually cooling and contracting as it radiates away the energy stored during its violent formation. The complex interplay between cooling, atmospheric chemistry, and internal structure will create a natural experiment in planetary evolution that will continue long after our Sun has exhausted its nuclear fuel. The discovery of this remarkable world has catalyzed international collaborations that demonstrate the global nature of modern astronomical research. Telescopes on multiple continents work in coordination to provide continuous coverage of target systems, while theoretical models developed by researchers worldwide contribute to our growing understanding of massive exoplanet physics. These collaborative efforts maximize the scientific return from expensive observational resources while fostering the exchange of ideas across cultural and national boundaries. The atmospheric chemistry occurring within ROX 42Bb's envelope operates under conditions that create natural laboratories for studying matter under extreme states. The combination of crushing pressures and intense temperatures produces phases of familiar materials that exist nowhere else in our cosmic neighborhood. Water, carbon dioxide, and other common molecules take on properties that bridge the gap between gas and liquid states, creating exotic forms of matter that challenge our terrestrial understanding of phase transitions. The magnetic field generated by this massive world creates electromagnetic phenomena that operate on scales approaching those found around small stars. Charged particles trapped within the planet's radiation belts accelerate to velocities that generate synchrotron radiation across the entire electromagnetic spectrum. These high-energy processes create a natural particle accelerator that could be detectable by sensitive radio telescopes, providing another method for discovering similar worlds around distant stars. The orbital mechanics governing ROXs 42Bb's motion around its host star involve gravitational effects that become apparent only when considering the immense masses involved. The planet's gravitational field is so strong that it measurably affects the motion of its parent star, causing subtle wobbles that could potentially be detected by precision astrometric measurements. These gravitational interactions provide independent methods for confirming the planet's mass and orbital characteristics. The thermal evolution models developed to understand ROXs 42Bb's cooling history have revealed unexpected complexities in how massive planets shed their formation heat. The efficiency of energy transport from the deep interior to the surface depends critically on convection patterns that operate under conditions of extreme pressure and temperature. These convective flows create circulation cells that could persist for millions of years, slowly mixing the planet's interior and affecting its long-term thermal evolution. The atmospheric structure of this colossal world exhibits layering phenomena that create distinct chemical zones at different altitudes. Temperature and pressure profiles derived from spectroscopic observations indicate regions where specific molecular species dominate, creating atmospheric strata with unique optical and chemical properties. The boundaries between these zones may host cloud formations composed of exotic materials that condense only under the specific conditions found in massive exoplanet atmospheres. The search for additional massive exoplanets continues to reveal candidates that may rival or exceed ROXs 42b in size and mass. Statistical analyses of survey data suggest that wide-orbit giants may be present around a significant fraction of young stars, implying that such worlds could number in the thousands throughout our immediate galactic neighborhood. Future observational programs will target larger samples of nearby stellar systems, potentially revealing an entire population of massive planets that remains largely unexplored. The discovery timeline of ROX 42b illustrates the patience and persistence required for modern astronomical research. Initial hints of the planet's existence appeared in observations spanning multiple years, but confirming its planetary nature required extensive follow-up studies using different observational techniques. This extended confirmation process reflects the incredible precision needed to distinguish genuine planetary signals from instrumental artifacts and background contamination. The implications of studying worlds like ROXs 42b extend far beyond academic astronomy into realms that could influence humanity's long-term future in space. Understanding how massive planets form and evolve provides crucial information for assessing the habitability of planetary systems throughout our galaxy. The gravitational and electromagnetic environments around such giants could either enhance or inhibit the development of life-supporting conditions on smaller worlds orbiting in their vicinity. The computational models developed to simulate the formation and evolution of supermassive exoplanets require some of the world's most powerful supercomputers and are driving advances in numerical methods that benefit multiple scientific disciplines. These simulations must account for complex interactions between gravitational dynamics, thermodynamics, magnetohydrodynamics, and atmospheric chemistry across spatial and temporal scales that span many orders of magnitude. As we drift toward the end of our cosmic journey through the realm of ROXs 42b, we find ourselves forever changed by what we've discovered. This magnificent giant, glowing with ancient heat in the darkness between stars, reminds us that the universe holds mysteries far grander than our earthbound imaginations could ever conceive. From its impossible mass to its lonely orbit, this world challenges everything we thought we knew about planetary formation, while opening windows into processes that shape countless worlds throughout our galaxy. Sweet dreams, fellow cosmic wanderers, and remember that somewhere in the vast expanse above us, this extraordinary planet continues its eternal dance through space and time.